We've all been promised this incredible future, right? Where AI isn't just stuck in some far-off cloud, but it's right here with us, on the edge, in our cars, our factories, our smart cameras. We're talking about real-time, instant intelligence. But there's a big, hidden problem that's stopping that future dead in its tracks. So many companies have this exact same frustrating story. They build a brilliant AI pilot. It works perfectly in the lab, but the moment they try to roll it out to hundreds or thousands of devices in the real world, it completely falls apart. So, what's the deal? Why is scaling AI so unbelievably hard?
Well, here's the thing. The culprit usually isn't the AI model itself. It's the hardware. I mean, just look at this. We're talking about a massive range of devices. Everything from these tiny little single-chip computers all the way up to super powerful GPU boxes. Getting one AI model to run perfectly on all of them? Yeah, that's the real challenge.
This whole situation leads to something we can call the pilot paradox. Your pilot project looks amazing because you're running it on a single, perfectly controlled piece of hardware. But a full rollout, that means deploying it across this messy, mixed-up fleet of devices that are all different ages, have different capabilities, and are sitting in different environments. What worked great on one device fails spectacularly on many.
Okay, so let's dig into this a little deeper. Let's look at these hidden hardware traps. Why exactly does this massive performance gap happen between that perfect pilot and the chaotic rollout? This diagram here shows exactly why this is so tricky. You see, the very same AI model runs into totally different problems on different hardware. A little mini PC might completely choke just trying to decode the video feed. A powerful GPU box might start to overheat and throttle itself. A specialized AI chip might have weird software driver issues. The weakest link is always changing. It's a moving target.
And all of this has very real consequences. This chart here shows something called P95 latency, which basically means how long does it take to get a critical alert out even in the worst-case scenario. On that powerful GPU box, it's less than a second. Awesome. But on a regular old mini PC, it's almost 4 seconds. And if you're talking about a security event, that difference is absolutely everything.
This unpredictable change has a name. It's called performance drift. And this is the key idea to really get here. It's when your AI's performance starts to degrade or just becomes totally random because of the specific hardware it's on, or even because of something as simple as dust clogging a fan and causing the device to overheat.
And that really brings us to the most crucial point. Nobody buys an AI model just to have an AI model. They're buying a reliable outcome. An alert that shows up 4 seconds late isn't a solution. It's just more noise. If you can't trust the AI to perform consistently, you literally can't build a business on it.
So how in the world do you solve this? How do you bridge that huge gap between a single, powerful AI model and the total chaos of all this different hardware? Well, what you need is something like a universal translator for AI.
The solution is called an execution layer. The best way to think about it is as a super smart middleman. It sits right between your AI application and the hardware, and its entire job is to guarantee something called performance portability, which is just a fancy way of saying it makes sure the AI runs exactly how it's supposed to, no matter what device you put it on. And this slide right here really nails the key difference. See, simple deployment tools like Docker, they just drop the exact same box of software onto every single device. And they don't care what that device can actually handle. It's kind of like shipping the same exact engine to a tiny scooter and a giant semi-truck. But an execution layer? It's way smarter. It actually looks at the device first, it understands its capabilities, and then it tailors the AI's workload to fit perfectly.
So here's a quick peek under the hood. The execution layer starts by creating what it calls a capability card for every device. Think of it like a super detailed profile of its strengths and weaknesses. It then uses that information to build a custom execution plan, choosing the right AI build and tuning it to deliver a reliable, consistent result every single time.
So how does this actually work in practice? Well, it's not a one-and-done kind of fix. It's a continuous, intelligent cycle that's always working to maintain peak performance. The whole system is basically in this constant loop of learning and adapting. Think of it like a self-tuning engine. It's always making these tiny adjustments to make sure the AI performs perfectly, not just on the day you install it, but months and even years later as the hardware gets older. Let's just quickly break down that loop. First, it profiles the device to figure out its true limits. Then, it selects the absolute best version of the AI model for that specific piece of hardware. Next, it adapts.
automatically fine-tuning things like frame rate to hit the performance target without crashing the system. And finally, and this is so important, it constantly verifies, watching for any of that performance drift, and it's always ready to roll back to a stable state if something goes wrong. It's like a built-in safety net.
Okay, so that's all the theory, but what about the real-world results? Let's look at the proof and see how this approach can shift the entire process from total chaos to predictable consistency.
I mean, the contrast here is just night and day. The before picture is a familiar nightmare for so many engineering teams. You're constantly fighting fires, doing manual tuning, and making expensive trips out to sites. The after is a predictable, automated workflow. It's really the difference between crossing your fingers and hoping it works, and just knowing it will.
And here's the cold, hard data to back it all up. Remember that huge 3.8-second latency we saw in the mini PC? With an execution layer managing everything, that latency drops down to a rock-solid 1.9 seconds. But you know what the most important column on this whole chart is? It's that last one. Every single device, no matter what it is, now passes the service level agreement. That, right there, is the definition of a reliable outcome. So the impact on the business is just massive. You get predictable performance, which means you have happy customers. Your support costs absolutely plummet because the system is basically healing itself. And most importantly, you can finally scale your AI business without scaling your support team and all your headaches right along with it. What this approach really does is unlock a future where deploying some incredibly sophisticated AI agent becomes as simple as downloading an app from an app store. You just choose the AI you need, and the execution layer handles the rest, making sure it just works on any compatible device you have. So you see, solving this hidden hardware problem is way more than just a technical fix. It fundamentally changes what is even possible. It removes the single biggest bottleneck to scaling AI in the real world. Which leaves us all with one final and very exciting question. When AI can finally run reliably anywhere, what are we going to build next?